Hope you've not heard well.
Thank you very much.
All right, good morning. We're going to start the first presentation for track 2. We have Tom Kopchak, and the title is the Domain Name System, Operation and Security.
Oh, good morning, everyone. Yay, you're not dead yet. That's awesome. I love to have an audience that's alive, so happy to see that. It's great to be here. My name is Tom. I'm a security engineer and operations team lead at Hurricane Labs. We're based out of Cleveland, so we made up the drive this morning. I know there's the whole Cleveland-Detroit thing. We're all kind of together with trying to see our cities rebound, so I like to see that there's good things going on in Detroit. Same for Cleveland. The one thing that was actually really kind of nice driving up on I-75 this morning was to see construction zones where there actually was construction going on. In Ohio, we don't have that. We were driving down the turnpike, and it's like 10 miles of just barrels, and then there's just one guy driving a truck down there. Like, here in Michigan, they had like backhoes, dump trucks full of like the interstate. It was awesome. So, good work there. I like to see that your construction zones are actually having things happen. So, on that note, I want to talk about something that's actually a little bit more relevant to what you guys are interested in, and security and DNS. So, how many of you here in some capacity work with DNS? I guess that's probably a bad question because you all have to use DNS in some capacity. But how many of you actually are responsible for administering or managing it in some way? Okay, there's a couple of you, so that's cool. Hopefully, this will just make you better at your job. For everyone else, I want to get everyone first on the same page and understand how DNS operates and functions. That's going to be kind of like the beginning of this talk, and then there's going to be a huge part near the end where we're going to talk about how attackers use DNS and different ways that it's leveraged for exfiltrating information, exploiting systems, kind of bringing down websites, all that fun stuff and the cool things that people do and talk about at security conferences. So, without further ado, want to, I guess, first start by saying why. Why are we talking about DNS? How many of you have heard, I guess to jump the gun a little bit, how many of you have heard this question before, if my thing ever responds? Is the internet down? Often times, there's many cases where no, it's just a DNS problem. Makes me think back to my college days. The apartment complex I was in used a certain ISP as their provider, and their DNS servers were being attacked. And everyone was just IMing me and saying, hey, like the internet here is totally not working. And I'm like, no, my internet's working fine. I don't understand what your problem is here. And eventually we figured out it was a DNS problem. The ISP DNS servers were getting attacked. I had my own DNS server in my apartment and didn't notice a thing. So name resolution is really important. Unfortunately, all too often, to users, name resolution is the internet. So if you can't go to google.com, they're not going to be like, what, I type in 74. something and I get Google? That doesn't make sense. Had someone I know who was trying to use the New York Times when their website was under attack and their DNS wasn't working. It really didn't work too well, even if he was trying to use the right IP addresses. So pretty much, if we are trying to use the internet, we need to have DNS, and those two technologies are so intertwined that it is really necessary for that to happen. And also, being an engineer, I really always want to know how something actually works. And I want to be able to articulate that to people, and I want people who work with things to be able to articulate that back to me. So if anything comes out of this talk, I'd like you to be able to better explain something that's a core internet technology to other people. So hopefully we all can do that in the next 45 minutes. And then, of course, since this is a security competition, or not competition, but a conference, we have the ops side, but we also have the security side too. How do we run this? How does it work? And how do we secure it? So it's going to be a fun next couple of minutes. So to start, I'd like to spend some time talking about the DNS structure, how DNS operates across the internet, and really lay the process of a request going from client to the different servers involved. First and foremost, DNS is really a globally distributed database. About how many of you work with databases in some capacity? decent number. How many of those that work with database spend a decent amount of time fixing those databases? It happens. Databases require administration. And a lot of times those databases are not global. They're just within an organization. DNS, on the other hand, it's one of those systems that is everywhere. And it's not administered by just one guy in his basement somewhere. There's so many different parties that work together to make DNS work properly. And really, this comes down to the fact that it's really kind of shocking that the internet even works some days. It's this hobbled together system of all these global servers and no universal source of information. And somehow all those things work together magically to allow websites to come up almost instantly. It's kind of really awesome. And one of the things that's key about DNS in the whole global scheme of things, there isn't really a single source of authority. If you are running a website and running a DNS server, you are the authoritative person for that. So it's really, you have your own piece as this whole puzzle of the internet together. Now I also want to spend a little bit of time covering some basic terminology so that we are all on the same page, and I'm going to use some of these terms later. First and foremost, up here, we have a local resolver. A local resolver is typically a DNS server that will exist at an organization. Usually your Active Directory domain controllers will function as DNS servers because AD and DNS are so closely tied together. You might have other DNS servers that are used for public external DNS. You might also have DNS servers that are used for DMZs that are secured differently. Also, you have the concept of a public DNS server. If your local resolver is not configured properly, it can very easily become a public DNS server, and that can be bad, and we'll talk about why. But public DNS servers are typically the ones that are provisioned by ISPs for use for their customers. Other great examples of that are Google's public DNS, the Quad 8, 8.8.8.8, or 8.8.4.4. Those DNS servers are things that people can use without having their own DNS servers set up. There's also the concept of caching, where a request that's made to a DNS server is stored for a period of time. The implications for this is it greatly reduces some of the load on the DNS infrastructure, and there's not as many queries that are required on a second-by-second basis. But it also makes changes take a little bit longer to propagate because caches have to expire and be updated across the internet. There's also the concept of a DNS root server. A lot of times the misconception with the root server is that it knows every answer about every domain there is. And that's just absolutely not the case. A root server only knows about the top level domains, your .coms, your .orgs, your .edus, and all of those domains are known where the authoritative name servers for those domains are. So a root server is really only one picture of the DNS puzzle. It just happens to be at the top of the DNS tree, which we're going to talk about in the next slide. Those root servers know where the authoritative name servers are, over here, and those servers will be able to tell where the name servers are that are for individual domains. So the .com, for example, would know about Google and other .com domains as well. So to lay out the structure here, I'm going to break down what a domain name actually does. The way I'd like to picture DNS in your head is a tree. At the top of the DNS tree, there's this invisible dot, which is called the DNS root. That's represented right over here. Now that DNS root is not something that you're going to type on a domain, but it's implicit in part of how a domain is understood. Coming off of that root, we have various top-level domains. Your .com, your .org, your .edu, your .net. All of those, it's expanding, by the day. They keep on adding top-level domains. But those are the ones that are directly known about by the root servers on the internet. From that point, authority is delegated from those authoritative name servers to different organizations. So for example, Hurricane Labs, we have a domain off of the .com domain, and we're authoritative for anything in that space. And since we have our own domain, we have the ability to have different subdomains. So picturing this as a tree, you have branches that branch out. You have your .com, for example, it has all those domains and every other subdomain. And this gets very, very massive very quickly at the scale of the internet. And now what I want to kind of go over is using that knowledge, the basic terminology and the structure, is actually walk through a DNS request from the time a client makes a request to the time the result is returned. The assumptions here is that there's going to be no caching that's done, no lookup yet. Everything was just turned on. The internet just started. So there's a client, and it wants to go to www.hurricanelabs.com. If you haven't done it, I'd highly recommend it. A little marketing blurb right there. Just got to throw that in there. So the client makes a request to its local DNS server. That's the DNS server at that organization. It's like, dude, I don't know about this Hurricane Labs place, but I'm going to try to look that up for you. So the local DNS server goes ahead and will send a request to the root server. And it's not asking at this point where hurricanelabs.com is. It's going to ask, where is .com? How do I get to these .com people? Whatever. So the root server, these are something that's hard-coded into the DNS servers. They know how to get to root servers. And the root server is going to say, hey, I know where .com is, I know where .net is, I know where .org is, I know where .edu is. Here, local DNS server, this is the authoritative name server for .com. So the local DNS server at that point has that information. It knows where the sources of information are for .com domains, but that's all it has at this point. Next thing that happens, the local DNS server is going to ask the top-level domain or the domain server, where is hurricanelabs.com? And the top-level domain server is going to look through its list of 4 domains in .com, Hurricane Labs, Google, Amazon, and Facebook, because that's all there are. And it's going to come back and say, hey, this is the authoritative name server for hurricanelabs.com. And this is how you get to it. This is its IP address. So the local DNS server is like, great, but I still can't get to www.hurricanelabs.com yet, so I better ask them how to get there. So the local DNS server will go ahead and say to our authoritative name server, where is www.hurricanelabs.com? And then what we'll see is we'll have a list of those local domains on our authoritative name server, and it'll return for www.hurricanelabs.com 74114. 44.111. Now the local DNS server knows that. Client still doesn't have the answer yet. That is the final step. The answer is returned to the client, and now the client knows where to send an HTTP request to. So that was 9 steps just to look up a single domain name for a website we wanted to go to. Just think about this on the scope of trying to view a page that has actually a lot of content in it. If you go to any sort of news organization site, you're going to have not only the content, you're going to have your advertisements, you're going to have your images, you're going to have your media. All of those often lie on separate domains. And each of those are going to require separate requests to be made. So you look at that, every time a new domain has to be looked up, with some caching involved and with some shortcuts, because you're not going to have to look up .com every time because everything's going to be going to the same server once you look that up initially. There's a lot going on just for name resolution. Isn't it kind of mind-blowing that this works as well as it does, given all the traffic and number of requests that are involved? It really is one of those things that just, you sit down and think about it, it's like, wow, it's kind of awesome that the internet functions. So the next time someone says the internet's broken, it's like, well, it really should be, just given the complexity of it, and then just go fix it, because your users aren't going to care at all how complex it is. Other things to keep in mind, there are not just one DNS server on the internet, and most organizations have multiple DNS servers. Generally, depending on what you're trying to do, but more often than not, you're going to want redundant DNS servers to return the same information. Now, if you're talking about it on the scale of like Google or Amazon, they're going to have DNS used for some form of load balancing. They're going to have multiple servers returned because there's just not one server that hosts google.com. But on a smaller scale, you would have multiple servers returning the same answer, often geographically distributed, so if one part of the internet has an issue, your secondary name server can still return the same results. However, if you need to use DNS for failover, you might want to load balance traffic differently. There's all kinds of things you can do with DNS to leverage that as well. So enough of that, how DNS works. I guess at this point, does anyone have any questions about that process before we start talking about threats? Perfect. You guys are all experts on DNS and will never have any other questions again. I appreciate it. However, DNS threats are going to be one of those things that this is one of those protocols that can be used for so many different types of attacks. And DNS is really one of those things that's hard to protect against because it's something that's so necessary and so common. So DNS is one of those protocols that pretty much everyone expects to see on a network. And it's one of those things that everyone kind of expects to not be all that harmful, because what bad could be done from just resolving names? That's the assumption that a lot of people have. One of the problems with this, though, is because it's something that's always available and relative or seen as harmless, attackers love to use these sorts of protocols for interesting sorts of things. And a lot of these types of DNS threats and attack vectors that we're seeing are really based on just using the protocol in a different sort of way, or leveraging a certain type of response or some other task in order to make something behave or cause a certain behavior. So really a lot of like the attacks that we see just in any sort of computer thing are the idea of taking something that's designed to be used a certain way and causing it to do something different. Great examples of that, your basic buffer overflows and your SQL injection type attacks, where you're using something that's available and tweaking it or changing how you're using it. So different types of DNS threats and attacks that I'm going to cover in this presentation, specifically these 5. We're going to talk about open resolvers, which are basically a configuration issue. And we're going to talk about the implications of that and how we can fix that, and also why it's a problem. I'm also going to cover different types of denial of service attacks using DNS, especially some of the distributed denial of service attacks. We're going to go over blind transfers, which can be often very useful if you're functioning as a red team or a penetration tester, or an adversary, either way. There's also the idea of register hijacking, and these were some of the attacks that were used in some of the really high-profile compromises, such as the New York Times and Twitter. They were victims of this. And then we're going to talk a little bit about DNS tunneling using DNS's covert channel, which is actually something Raphael mentioned in the keynote just a little bit before this presentation. So we're going to kind of step through all those, and at any time, if you have questions about this, just feel free to interrupt me and we can cover that as well. So open resolvers are one of those common misconfigurations where the DNS server goes ahead and returns results for a domain where it's not considered an authoritative server. This is one of those cases where something is leveraged by an attacker, and it's an extra functionality that can be used for evil things, more or less. So this happens a lot, and I'm going to talk about how we're going to test for this, and then why it's bad. So I would encourage anyone who is using a DNS server or running a DNS server to run these sorts of tests and kind of see how it behaves. If you're using Windows to test for an open resolver, you can use the nslookup command. This is what you should see if you're trying to run this against your DNS server and you're trying to see if it's configured correctly. So in this case, we have the nslookup, and I think there's a way I can go back. I think there's a way I can circle this because I like to point. Okay, so we have the server that you specify here in the nslookup command, which would be your DNS server's IP address, and then you specify the query. So in this case, let's just say that you are asking your DNS server, hey, what is the IP address of hurricanelabs.com? Then you're going to see that this should actually say Hurricane Labs here and not Google, but your DNS server, if it replies saying, hey, I can't find hurricanelabs.com, this query is refused, this is what indicates that your server is not functioning as an open resolver. Now on Windows, if you want to see what happens when it's behaving incorrectly, you just do the same nslookup command, and then you look for hurricanelabs.com, and if you get a response here from your server, even though you're not authoritative for hurricanelabs.com because you're not hurricanelabs.com, that means that your resolver is an open resolver. So any questions about that sort of behavior? Okay, that's good. There was a time I was giving a talk on this, and there was some person in the back kind of typing away on their phone, and they just kind of had that depressed look. And after the presentation, I was talking to them, and they're like, yeah, I got to go home and fix this because I'm an open resolver. So I fixed one thing on the internet. That's my personal claim to fame. So also on Linux, there's ways of doing this using the dig command. So in this case, I'm going to use an example against our Hurricane Labs name server, where I'm going to dig against notns1.hurricanela.bz. They were getting a little cute with the domain there. But looking for google.com, we see a question section here where I'm looking for an A record. And I'm getting this error right here, recursion requested but not available. That basically means that my client is saying, hey, I need you to recursively look up this domain. And the server that's handling DNS is like, dude, no, go away. That's what you want. Now, on Linux, if you're doing this again, you run your dig command for Google, and you see a whole bunch of A records that come back, or address records. In that case, there is a problem, and this right here should say hurricanelabs.bz and not 8.8.8.8. Little typo on the slide there. But if you're getting results for a domain that you don't own, that's a problem. Now, if you happen to be Google, that's okay. This would be legitimate. But if you're not running Google's DNS servers, that's a problem. So probably at this point you're wondering, why is this bad? Well, attackers love open resolvers. And they use open resolvers for a whole bunch of denial of service attacks because it's a great way to send a lot more traffic from a single bad client to a target without having to have a lot of bandwidth up front. So to lay out how this actually works, there is the attack amplification process that an attacker will use. So basically what you have an attacker right here, and like every attacker, they have a botnet because that's what attackers do. And they simply need to send a request to each of these hosts on the botnet that says, hey, this is a list of all the open resolvers that I want to use for this attack, and this is the victim that I want to send all this traffic to. So all these botnet hosts, what they basically do is spoof the source IP address of their DNS request as this guy, the victim server. And all of the traffic from all these botnet hosts to these open resolvers, instead of being returned to the hosts in the botnet that originally requested, all that traffic gets sent back to this victim server. So essentially, the only thing the attacker in this case needs to send is a target domain and a list of domains that they're going to use for relaying this attack. So by being an open resolver, you're not necessarily being the target of a denial of service attack. You're being a contributor to a denial of service attack. And unfortunately for the victim, this is just a massive influx of DNS traffic that they didn't request and can't really do much about because it's all flowing in. And typically the type of requests that they're using are not just a general A record. We'll be using a DNS any request, which is one of the largest DNS types of packets, and basically returns all the domains that are hosted by that server. So for a single botnet host making a small query saying, hey, this site, tell me everything, and oh yeah, send all the results to that poor guy over there, it results in a massive denial of service attack that's quite difficult to stop. And speaking of stopping it, I'm sure that's the question you're asking right now. How do we stop this? Well, I'm glad you asked. Fortunately, every DNS server has a switch on the front that you can use to turn off recursion. Just flip that and you're good to go. Unfortunately, not quite that simple, but it is a matter of having proper configuration. You'll want to make sure that recursion is disabled on your DNS servers that are public facing, just so that you don't have cases where it will return results for something that is not authoritative. And that's really a simple configuration change. And if you test this against your DNS servers and you see that sort of a problem, I would encourage you to change them so that you don't contribute to denial of service attacks on the internet. Okay. Remember, you aren't an ISP, unless of course you are. Any ISPs in the room here? Okay, good. Then you're not an ISP. So only reply or provide responses for domains that you own. You don't want to be the nice guy DNS server on the internet, because we all know what happens to nice guys. They are involved in distributed denial of service attacks. That's how it works. At least that's what I've always been told. Other things to keep in mind: blind transfers. These can be bad. What a blind transfer is basically one of the core functions of DNS is the idea of doing zone transfers. So you'll have a primary DNS server and you'll have secondary DNS servers. Within an organization, in order to replicate that, they'll need to transfer zone information. Some of this can be inter-organizational, some of this can be intra-organizational. So if you have another third party or an acquisition, they need to have zone information for other sites. So this distribution of DNS information and records is something that's built into DNS server operation. But let's just say, hypothetically, that you're not one of those organizations or entities that should legitimately have this information. Let's just say you're like pen tester dude, and they want to have that information. So if you do a blind transfer and you get all the information, you already pretty much have the phone book to an organization. So saying that I'm trying to break into a company, and I get a DNS record for mail.company.com. What are you guys going to think that is? Mail server, yes. What about intranet.company.com? Probably an intranet page. E-commerce database.company.com. See how this is? You don't even have to even run a scan at this point. You already kind of know what to target at different types of systems. So I know, for example, that we have seen many cases where this has been available, and our pen testing team has had a lot easier job, at least with their initial recon, by having a blind transfer happen. So it's not going to necessarily stop something from happening, because an attacker can still figure out a lot of that information and just make their job easier. And really, you don't want to make the attacker's job easier, because they have enough ways to get in anyway, and just trying to reduce that can be definitely useful. Also, there's domain hijacking. This one can be annoying, and it can also be difficult to stop. It's been used in a lot of the high-profile ones, such as the New York Times attack and the Twitter attack. And this is really at the core a social engineering attack. And it's not against a party that is in your organization, but it's the registrar that you have to trust with your domain information. And basically the way that this works is the bad guy will call up your registrar claiming to be you, and basically say, hey, so you know the NewYorkTimes.com? Yeah, our DNS servers, we're moving them from New York and New Jersey and the one that's in California. Those all live in Russia right now. So can you just change those names for me? Point to those IP addresses. Everything will be cool. And the registrar's like, sure, that sounds cool. Anything else you want me to do? Oh yeah, change over Twitter too. And they're like, okay, that's cool. So basically you have a situation where all of the DNS requests that should be going to name servers for the New York Times are now actually going to DNS servers in Russia. And nothing good can come from DNS servers hosted in Russia. But besides that, they are now saying, instead of New York Times being the actual IP addresses for there, it's a page that looks like the New York Times, but has a whole bunch of embedded malware in there. So that sort of thing, if you're on the scale of an organization that large, it can be very effective for having a huge number of users get compromised with something. Unfortunately, one of these things is a little bit difficult to stop because you're relying on the security implementation and the procedures of your registrar. There are methods where you can lock a domain so that you can at least be notified of changes, but even then, attackers, they have fax machines, so they can get around that a lot of times. And also, things to keep in mind with this is that it is one of those third-party sort of things, so you can't control it. One of the things that I found is a little bit beneficial for this is more of just an alerting sort of process. So you can watch for changes that happen to your registration information. So if your records are ever modified and it's not you, that would be something you can alert on and take action on and basically limit the scope of the impact of this. But even then, it's one of those, since you don't have the chain of control, it is a lot more difficult. And finally, and this kind of touches on what we talked about downstairs, the use of DNS as a covert channel or for tunneling. And this is awesome and evil at the same time, because one of the assumptions is that DNS is able to be used anywhere on any network. And DNS relies in a situation where there is trust that's built from servers to other servers, and that information needs to be relayed from different types of servers. So when you're going, we can't necessarily restrict DNS from functioning and keep DNS from happening and allowing DNS tunneling to function. So the way that this works is that you have a client that runs this DNS tunneling application, and the DNS tunnel server on the internet is listening for these specially crafted DNS packets. And basically the client sends specially crafted DNS requests to the DNS tunnel server by means of the existing DNS structure through the means of actually legitimate DNS queries that can be handled by DNS as expected. So it's all RFC compliant. It's nothing like obscure DNS traffic that doesn't always work. This is one of those things that allows it to be used in almost any organization. And if DNS is allowed, you can use DNS tunneling to exfiltrate information. I've seen cases where people are using this for not only trying to just get information out, but let's just say you're faced with a captive portal, like at an airport or something like that. Using DNS tunneling, you can use DNS to actually surf the web. It's not going to be fast, but it's going to work. So the idea here is, how can we identify when DNS as a request, it's like a single DNS request is more than just a DNS request and actually carrying more information. So this is kind of an example of what a DNS tunneling traffic or tunnel looks like in terms of DNS queries. Let's just say I'm an attacker and I own the shadysite.info domain, which actually was available the last time I checked, and it's really something I would just want to buy because it's a great example domain. But I have this tunnel.shadysite.info, which is my DNS tunnel server. What I do is I start sending all these obscure-looking gibberish type queries to it, and it's going to go ahead and basically allow requests to this domain, which is not really a DNS server, and I'm going to have results that are returned in what look to be DNS format. But in this information that's here is encoded information. So basically that encoded information is carrying whatever payload I want to have. One of the things to keep in mind, tunnel.shadysite.info is probably not the best example for having something that you are using the payload of the DNS request as a actual carrier of information. You want the shortest domain that you can possibly come up with, because you're limited to 255 characters in a DNS request. So that's the extent of your payload. Anything you take away from the right side here, it just makes your throughput capacity even slower. Other things to keep in mind is that you're going to see a significant increase in these DNS requests to a domain, which is something that can be used potentially for alerting purposes. And that kind of goes into how we might be able to stop this. There isn't really a good answer that I've consistently been able to find. There are different options. Behavior analysis is probably one of the most effective for this, but it's also one of the most difficult. Basically, you have a bunch of clients that are going to make DNS requests all over the place, and what you're going to see in DNS logs is a significant increase in the amount of requests that are going from your DNS server to a single domain. Now, I've tried examples of this where I've run a tunnel through, logged all the DNS, threw it into, even I've thrown it into Splunk, for example, and use anomaly detection to try to figure this out. It works great when there's only one DNS thing that's in the logs. As soon as I actually put like real traffic in there, it's just like, nah, I'm not going to find it immediately using the automated stuff that's already there. So there's definitely areas for improvement on trying to not whitelist, but to actually see this sort of anomaly in the behavior and alert on that. Yeah, sure.
So a couple ways that I've seen this stop is A, for detective purposes, looking for massive amounts of queries, because usually people only query once in a while, it's the second threshold.
Yeah.
And then B, looking for DNS queries to other than DNS servers. So it's having whitelist of DNS servers, we send out to Google, external, whatever it may be, and then preventing anyone else from going to my home. Right? So that's some sort of VPN for DNS.
Yeah, so to kind of echo on some of that, like one of the normal behaviors for this, and a DNS tunnel program that I've seen and worked with is called Iodine. The reason it's called Iodine, port 53 is DNS, Iodine 53 on the periodic table, little science joke there. But basically, this program, it makes the DNS request outbound to the server directly first. I have seen places where they understand their network to the point where if a rogue DNS request happens, that is not something that they expect. It's something that immediately triggers an alert, and that's something they take action on as a potential someone trying to exfiltrate data. The chances of a lot of environments being tuned that way, very slim. It is a lot of work, exactly. That is something that can work, but it is the case where you take a single packet is your only chance of trying to find this sort of thing if that's all you're doing. So a lot of times, people are going to be saying, oh, that's just a DNS request that happened, not a big deal. The other thing that I've seen where we're talking about, like in your case, you're allowing only DNS to go to whitelisted DNS servers, for example, and sending people to Google. This will still work because your DNS, you have all the DNS backend to make that request go through the internet, basically. So I'm not sending a DNS request directly to my house, for example. I'm actually sending it through the organization's DNS server, through the, whatever they're using upstream, if they're not using the DNS structure. And then I'm also going from that to my house and then back through the whole tree. So it is a legitimate DNS request. And as far as the DNS servers are, it's not like you can use the DNS server as an application layer firewall for DNS because it's RFC compliant traffic. So that's where this gets a little complicated. You're not going to be able to stop it with your DNS server. If you did something like thresholding DNS request volume, that can work. If you alert on a DNS request that's above a certain number of characters, because I think doing kind of analysis on this, most normal web browsing, getting over like 140 characters is kind of rare. Whereas these programs will start with like 250 and then step down. That's anomalous behavior. So I've caused interruptions in these sorts of things in a lab by like using an IPS to limit all DNS requests to like 180 characters. Most of the time that's going to make the tunnel very, very slow and something you can alert on to ramp up before it gets to the point where it detects that as the maximum value. And then also while trying to keep internet functionality still working so that you're not blocking or breaking legitimate DNS requests. One thing that would work absolutely well would be whitelisting domains, but it's psychotic because you're back to the zone file days where everyone had all the domains listed out. There are vendors that claim they have detections for this, and I still need to test them. Things that I've done in the past have failed in the lab, so I can't say anything that I've out of the box seen as a vendor saying this works has actually behaved that way. But if I find one, I'll definitely add that in here. So it is an ongoing area of research, and I think it's something that is an area that we can definitely improve on and learn more from. So it's an interesting sort of thing. And with that, basically that wraps up what I have, and hopefully you can leave this presentation understanding a little bit better how the internet works. So let me know if you have any questions, and thank you very much for your time. So the question was, if I got that correctly, do I recommend any tools for DNS tunneling testing? In the lab, the program I've worked most with was the one called Iodine, which is probably one of the most standard DNS tunneling tools. It's actually really easy to use, and I think it pretty much just works on Linux fine without a problem. I don't know if there's a Windows port for it. Everything I did was on Linux for that. But it's command line. You run it on a server, you run it on a client. You make sure all the DNS stuff works to allow it to communicate, and you basically have a tunnel that fires right up. So it's really easy to play around with, and then can definitely be something you can experiment with. Yeah, you're welcome. Anything else from anyone? Well, thank you very much. Well, yeah.
You think that for the DNS servers will have a list of the names of the headquarter DNS port in the internet to be able to resolve all the names.
So the Google DNS server is actually going to be doing the same thing like a local resolver would do in that case, with the exception of it's probably going to have a lot more significant cache than your local one would have. So obviously there's a lot of people that are hitting Google's DNS server. It's going to know where most of the top sites are going to be without having to go through the process. But it does have a cache that expires too, so it's going to have to still periodically check those systems as well. But at least from a structure procedure, it does the same sort of thing.
On a larger scale.
Yeah, on a larger scale. And it has to do that because it's not going to just know. It's going to have to go through the same process as any DNS server would.
Thank you.
Yeah, you're welcome. Anything else from anyone?
Some of the commercial products that you use, do they use like DNS bandwidth monitoring?
There are different IPS products that have DNS protections. One of the ones I've worked with is like Checkpoint's IPS. There are a number of IPS protections that are in there. So you can actually threshold the length of like a DNS request using that.
But if you have a client that's sending multiple requests, I would expect you to be allowed back and forth.
Yeah, so you could do something where you can limit the amount of, like, the same sort of thing you do for any sort of traffic limiting, like rate limiting. You could apply to DNS as well. But it's one of those cases where how much of an impact you look at, you have to understand like what a base traffic use looks like for a user and what's actually considered an excessive amount. And in the case of, if you're actually trying to threshold that, an attacker can dial that down just like you could for like an Nmap scan, for example, and just go with a slower approach to send out that. So it's one of those cases, if you need to stop that, you actually have to alert on it and take action when it's happening. Yeah?
Do you know if DNSSEC helps prevent any of those attacks?
Because DNSSEC isn't mandatory, like the signing wouldn't necessarily stop the tunneling or anything like that. It's more of a signing to make sure that the things are legitimate. If you had like DNSSEC for Twitter, for example, and it got pointed to another registrar, that might be something that you could at least say, like in your browser, it would say, hey, that would be more of like a it's the thing that's based on DNSSEC. It's like Dane. Someone said that. That would be possibly something that could pick up on that sort of thing. But your average internet user, I don't think, is going to benefit from something like that. DNSSEC is just not widely adopted. Everyone talks about it, but it's one of those things that just kind of exists, I guess. Yeah.
How do you feel about OpenDNS and their blacklisting, whitelisting capabilities on business?
For businesses, it can definitely be a benefit. I know organizations that use that as not necessarily their primary DNS, but like their backup DNS if their internal DNS fails. There's different types of DNS. In terms of like quality of that, yes, that's like a managed service. It has security implications. It can be definitely beneficial. Google's DNS, for example, is just going to be raw RFC compliant. They're never going to tell you different results. At least that's what they say. Take that however you please. But Google's DNS is never going to say, hey, I'm going to tell you this IP address for a non-existent domain. It's going to give an NX domain record. And then at the bottom, like below the ground floor, you have your ISP DNS, which is unreliable, often attacked, and sends bad results sometimes. I've seen companies compromised by using ISP DNS servers because they get popped. Next thing you know, Google is now this malware site. So in terms of legitimacy, I would go with like either your own DNS, OpenDNS, Google, as those as your choices, and try to avoid the ISP DNS if at all possible. Okay, anything else? Well, I appreciate it. You guys have been a great audience, and enjoy the rest of the day.